Thermochemistry is the branch of chemistry that is primarily concerned with studying how heat can be evolved or absorbed by a chemical reaction. Now, this is something that I'm sure everybody has experienced at one point in time or another. If you've ever held a warm cup of coffee and felt your hands get warm, or put your hands over a fire, okay, and warm them by a campfire, these are examples of a chemical process leading to the evolution of heat. Okay, so one way that we can think about that is in terms of the heat traveling. Okay, so let's say we have some type of container. Okay, this container is where we're going to carry out the reaction. Okay, and we're going to call that container the system. This is the part of the entire universe that we are interested in when we're studying this reaction. Everything else in the universe is known as the surroundings. Okay? And in any chemical process, one of two things is going to happen. Either heat is going to be generated and transferred to the surroundings, or heat is going to be absorbed from the surroundings. Okay? And the fundamental thing that we need to remember, so fundamental that we actually have a special name for it, we call it the first law of thermodynamics. What the first law of thermodynamics tells us is that the energy of the universe is constant. Okay, so let's take a step back here. When we looked at this chemical process that was exchanging heat with its surroundings, when you think about it, if the system is the reaction or process that's taking place and the surroundings is everything else, that means that the system plus the surroundings is going to be equal to the entire universe. Okay? So one way that we can formulate this mathematically is by saying that the energy of the universe, which we will symbolize as delta E, okay, is equal to 0. Okay, so the energy of the universe does not change. You can't create energy, you can't destroy energy. Okay, now here's where things get a little bit interesting. You see, we know that in a chemical process that the energy of the system is changing. And we know that the energy of the surroundings is changing. And we know that the system plus the surroundings gives us the entire universe. Okay, so any change in the energy of the system plus the energy of the change in the surroundings must be equal to the change in the energy of the universe. Okay, but we already know that that equals 0. Okay, so any change in the energy of the system plus any change in the energy of the surroundings must be equal to 0. Okay, and if I rearrange this a little bit, what I wind up with is that any change in the energy of a system must be equal to the negative of the change in energy of the surroundings. Okay, which looks like, this some equation, but what's really important here is what this equation tells us. Okay, this tells us that any heat that leaves the system goes to the surroundings. There is no in between, there is no limbo. Okay, any heat that goes from the surroundings must go to the system. Okay. Okay, we find a really cool application of this when we think about something like a cup of coffee. Okay, if I take a hot cup of coffee and put it on the countertop in the laboratory and let it just sit there, okay, we all know that that cup of coffee is going to cool down. But have you ever thought about the fact that that energy that was in that cup of coffee, in the form of heat, was being transferred to the rest of the room, actually the rest of the universe? So by letting that coffee cool down, what we were actually doing was warming up the rest of the universe. Okay, now granted, the rest of the universe is a fairly large space, right? So we don't expect that we would see the temperature of the universe rise very, very steeply. It wouldn't be perceptible at all. In fact, even the temperature of the room that the coffee was in, you wouldn't be able to detect any increase in temperature. Okay, but it does work that way, and it's important for us to realize this because many of the concepts that we're going to be covering, especially calorimetry, is dependent upon this principle. Okay, now we're talking about the change in energy of the system. Okay, from now on, I'm going to simplify this a little bit and just refer to this as the change in energy, or delta E. And this is because the system is really the only thing that we can truly measure. We can't measure the rest of the universe. So we place our focus on that system, which is why it's so important for us to be able to define that system. And if you get the chance, I would highly recommend going back into your textbook and reading about the three different types of systems to understand how energy and matter can transfer through different types of systems. Okay, so we're talking about the change in energy of the system. Okay, there's only two ways that the energy of a system can change. Okay, the first is via heat. Okay, the release of heat or the absorption of heat. Okay, and we symbolize heat by a lowercase letter q. Okay, so if heat is being absorbed, okay, then the value of q is going to be positive. Okay, if heat is released, the value of q is going to be negative. Okay, so you can see if heat is being absorbed, that means that the change in energy is going to go up. So delta E is equal to a positive value. Okay, assuming nothing else changes. Okay, but if heat is being released, then the energy of that system is going to decrease. Okay, so that's one way that we can do that. Another way that we can transfer energy is through work. Okay, and we symbolize work with a lowercase letter w. Okay, now you might remember from an earlier physics class or maybe a physical science type class that work is actually defined as a force applied over a distance. Okay, so work equals force times distance. Okay, but in chemistry, we don't have an organized particle moving in one fixed direction, applying force in that direction. Instead, what we have is the opportunity for work to be done through expansion, okay, and compression. Okay, so instead of looking at a force being applied over a distance, when we're talking about thermodynamics, we talk about work as being a change in volume against a pressure. Okay, and notice that there's a negative sign in front of the pressure. And the point of this is to make sure that we maintain our sign conventions that we're using in order to keep heat and work kind of on the same playing field. Okay, so when you think about it, if I have a reaction that maybe produces a gas, okay, the volume of that container, if it can, is going to increase. So it's a positive value for that change in V. Okay, and if V is positive, pressure is always positive. So we take the negative of a positive and we get a negative. So work will be equal to a negative value. Okay, and if work's equal to a negative value, okay, that means the change in energy will be negative. Okay, now when we have something that is producing a gas, we say that it's undergoing expansion. It's pushing back against its surroundings. So when we say that the system is doing work on its surroundings, what we're saying is that the system is expanding and pushing back on the surroundings. Okay, the opposite of that is compression. Okay, and in compression, the change in the volume of the system is going to be a negative value, which means work will take on a positive value. And if work is positive, holding all things equal, the change in energy is going to be positive. Okay? So these are the two ways, the two currencies by which energy can be transferred from the system to the surroundings. Okay, so if that's the case, then we can say that the only way that we can get any change in the energy of the system is through work and heat. Okay, so the change in energy is going to be equal to Q plus W. Okay, just make sure that you're very careful in keeping track of the signs. The sign conventions are vital to doing these calculations properly. Now, as you can imagine, a reaction that, well, pretty much any reaction is going to be either exothermic or endothermic. In other words, taking in heat giving off heat or taking in heat. But then just that very process of taking in heat or putting off heat is actually changing the temperature of the air around that reaction. Okay, and that has an impact on pressure. Okay, so there's always going to be some kind of heat being transferred and some work being done. Unless, of course, you're in a container that is not capable of any expansion whatsoever. But it would be nice if we had a thermodynamic property that kind of ties these things together. Not just ties them together, but allows it to be experimentally measured as well. Okay, so just measuring the delta E is not a possibility. But we can measure the heat being given off by a reaction. Okay, so that's what we're going to look at. That thermochemical term that kind of puts it all together is what we call enthalpy. Okay, we symbolize enthalpy as delta H. Okay, so the enthalpy for a process is actually derived from the energy equation that I just showed you. So first I want you to consider two circumstances. Either we have a system with constant volume, or a system with constant pressure. Okay, when we have a constant volume, that means the volume can't change. So this reaction is taking place in a steel container that will not bend or flex or anything like that. Okay, and because of that, we can say that the change in volume is equal to 0. Okay, whereas in a constant pressure system, okay, we have the ability to do expansion against the surroundings. Okay, so delta V can either be positive or negative. Okay, but of course, pressure is going to be a constant. So delta P would be equal to 0. But we haven't really dealt with delta P, so I'm not going to worry about that right now. Okay, so what I'm going to do now is I'm going to look at the constant volume system and rewrite the energy equation that I gave you previously. So energy, we said, the change in energy is equal to heat plus work. Now we said earlier on that work is equal to the negative of pressure times the change in volume. Okay, so the change in energy is going to be equal to Q minus P delta V. Okay, and what I'm going to do is I'm going to take this heat here and I'm going to get it by itself. So I'm going to swing that around to this side, and we get Q equals delta E minus P delta V. Okay, so now we know that the delta V is going to have to be equal to 0, which means that wipes out this entire term. So the heat at constant volume, and we indicate that by putting a little v there, is equal to the change in energy. Okay, but it's different when we have constant pressure. Okay, when we have constant pressure, delta E is going to equal, I'm just going to pull from what I did over here, Q minus P delta V. Okay, we know this is Q at a constant pressure. Okay, and then I'm going to rearrange this again. So Q at constant pressure equals the energy change plus what we call pressure volume work. Now, if you read in the chapter in your textbook, you would have read about state functions. And it turns out that even though Q is not technically a state function, it is being determined by state functions with the delta E, the delta V. Okay, and since it's being determined by state functions, effectively it acts as a state function. Okay, so we rename this now as delta H, which is equal to the change in energy plus P delta V. Okay, and we can talk about enthalpies of all different types. We can have the enthalpy of a reaction. Okay, we can have the enthalpy of specific reactions like combustion. Okay, we could have the enthalpy of solution. So the amount of heat that's being given out or taken in during the course of a reaction, of a substance being dissolved in a solvent. Okay, so there's many of these out there. Okay, and in our next video, We'll talk about how we can do calculations to figure out the enthalpies of reaction or combustion or whichever process it is that we're looking at.